Okay, so in our final step, step 3, we're going to determine how much time it takes for the shutter arm to close. And so we've got our system here where L represents the length of the shutter arm. We've got that small distance between where the shutter arm connects to the housing and where it connects to our spring. We've got our force going down. We've simplified the problem by making some assumptions. So the first is that our spring force acts perpendicular to the lever arm, defined by that value of r. So really it's always acting on a right angle, and that just allows us to remove our cosines and our sines. All right. The next is that we're ignoring the opening of the mechanism. So here we have our housing again, all right, and we're going from all the way at this open position. All right, and you'll see that your shutter arm has a little piece of material that stops it from opening any further, and we're just modeling it going from that open position to that closed position. We're not concerned with this movement from the open to the close, from the closed to the open, just the open to the close. All right, so we're just looking at this one direction. Okay. We assume that the spring has some sort of initial pretension. We are looking at the mechanism opening from 150 degrees to 180 degrees. And so what that means is if we actually take our system here and we analyze specifically the points in which the shutter arm and the spring attach, so we're looking at these 2 points, and we put them in a relative position where if this is our central point, the point in which the shutter arm is attached, if we have it in that closed position, all right, you can see that that other attachment where the spring attaches is at 180 degrees to this point where the shutter arm attaches. If we then swing it open, you'll see that that point moves to a 150 degree angle relative to that initial plane that we had it on. Okay, so we're looking at it in the open position being at about 150 degrees, and then as we close it, if I close this again, all right, and I bring it back down, now we see that it's about 180 degrees. Again, we're looking at these 2 points where the shutter arm and where the spring attach. Okay, so we've got our open position, just noting this here, equal to 150 degrees, all right, and our closed equaling 180 degrees. Okay, all right. So what we're going to do is do a handful of calculations here in order to determine that amount of time that it takes to close. The first thing we're going to do is model the force as a function of the angular movement, and that's our force theta as a function of theta that you'll see in the overview document. All right. Now, in order to do this, we're going to have to create another plot like we did in step 1. This time, however, we're looking at not the relationship between force and the change in length of the spring, but force and our angular position. Okay. Now, where do we start? There's 2 things that we know. The first thing is we know what our open and closed is. We have it right here, 150 and 180 degrees. So we have our 2 points, 150, 180. Note that I'm putting 150 here and 180, but you do want to keep these in SI units, so don't forget to convert those to radians. We also know based on step 1 what the force is at the open position, and we know what the force is at the closed position. Okay? And since we can make a connection between those 2 points, we can use those values for force because they're in newtons and it's not like they're going to change whether it's in terms of the change in x of the spring or our radians, right? So we can use those values and we can actually use those points to create another linear plot. Okay. Now we can determine what the relationship is, and you can note that this is another linear relationship, so we will get a y equals mx plus b, where in this particular case our y is our force, okay, and we've got our slope, and then our x in this case is our theta, and of course we may have a y-intercept. We're not sure. You'll see that you will get a downward slope, so where it intersects our y-axis, you will see that you will have a b value there, and it will not cross through 0, 0 in this particular instance. Okay. So what you're going to note for one of our equations is that our force as a function of theta is going to be constantly changing, and you're going to need to recalculate this based on where you are in this range from open to closed. All right. Now, you're given a series of equations, and one of them does utilize that relationship of force as a function of theta as we're moving on to our next question here. Okay. And what you'll see is that we've done the derivatives for you. So the first equation that you have, and this is actually labeled as equation 3, is our angular position. Okay. The first derivative, all right, of our angular position, if you recall from physics, and we've labeled it as theta dot, you may know it as theta prime, all right, is our velocity. And our second derivative, we've labeled as theta double dot or theta double prime, is our acceleration. Okay, so all of this should be familiar to you from your physics classes. And so we've provided the equations for each one of these, and I'm going to break them down really quickly. All right, and that our theta, our position, is equal to 0.5 times our velocity today plus our velocity yesterday, okay, times our change in time, all right, plus our old position. That's our labeled as equation number 3 in the overview document, but that's our first equation that we have here. And so you'll see that there are then 2 equations for acceleration that are provided to you. All right, the first one is that force as a function of theta. Again, this is constantly changing based on this equation right here. Okay. We multiply that times our r value, which we were looking at earlier, the distance between our shutter arm and our spring. All right, we're going to divide that by our mass times our length squared. And the length is the length of the shutter. The mass is the mass of the shutter. Okay. We also note that our acceleration is equal to our velocity today, right, minus our velocity yesterday, divided by that change in time. Okay. And just for the calculation's sake, we're going to analyze this using a change of time of 0.0005 seconds. All right, and that is SI units or seconds. Okay. Now, all this becomes is a simple algebra problem, all right, where you have a number of unknowns that you're trying to determine. Okay. We now know what our force and our theta are because of our relationship that we saw up above. Okay. We know our mass, we know our length, we know our r. Okay, so we can solve for our acceleration. Okay. We can use that acceleration to determine what our velocities are using our change in time that we just noted of 0.005 seconds. And that's just arbitrary. We're using 0.005 seconds because we want to record the change every 0.005 seconds so we can determine as closely as we possibly can how much time exactly it takes for our shutter arm to close. All right. Now there's a couple things that we can use in order to use these equations to determine what our final time is, and that's really what we're trying to solve for, is our time. All right. First thing to note is that our initial position, okay, so that first position, our initial position, okay, is 150 degrees. Okay. So let's remind ourselves of that, and we can use that value to help with this calculation. The second thing we know is that we are assuming that the system, when it is in the open position, when it actually strikes this piece of plastic and stops, all right, before it starts to close, its velocity is equal to 0. Okay? So we know that our first velocity yesterday is equal to 0. Okay. Now, what I mean by today and yesterday is what we are going to be doing is analyzing the system. So we're going to be doing a simulation of calculations here, checking every 0.005 seconds how far has this shutter arm closed, all right, and how long does it take to go from 150 to 180 degrees. Okay, so our velocity yesterday is whatever the velocity was 0.005 seconds ago. So our first velocity 0, as I was just mentioning, is always going to be equal to 0. And if it's equal to 0, that allows us to solve for our first velocity after 0.005 seconds. and then we can continue to calculate these two values by taking whatever our previous velocity was and putting that in for our yesterday velocity. We can solve for our new velocity another 0.005 seconds later on. Okay. Once we know those values, again, we can tie it back to our position and identify how far along our shutter arm has gone. And again, we're basically creating a simulation. And so what you're going to want to do in Excel is basically create a table where you have a column for your position, a column for your acceleration, a column for your velocity yesterday, a column for your velocity today, and then of course your time. Okay. And this way you can calculate every 0.005 seconds, 001, 0.0015. All right, how long does it take to go from our first position of 150 down to our final position of 180? And then you just look across and see how much time has elapsed at this position. And that'll allow you to determine how much time it took for your shutter arm to close. You'll answer a couple questions about this. Okay. The first one will be to plot your angular position, that's this column right here, versus your time, this will be this column right here, to look at the relationship. So that's just a simple plot where you have your angular position and your time. Time will be here, angular position here. And I'm not going to plot it here, but you'll plot it and determine whether or not that is linear. So a linear relationship would be like the one we saw up above here. All right, is it linear or does it curve? And if it curves, why is that the case? So explain what the movement is and why you think you see that type of movement. And then finally, is the velocity 0 at the end of the simulation? All right, so we've got our shutter arm that's coming in here. Again, it's going from this open position to this closed position. So when it gets to this closed position, is our velocity equal to 0? And explain why you believe it is or is not equal to 0. And you have fully demonstrated a simulation and a modeling, a physics-based mathematical model of the shutter arm closing for your disposable camera.